Hola.
Okay.
Okay, so it is a pleasure to introduce Albert. He is visiting us for a couple of days together with Robert that will give a seminar after this one talk, a regular talk. So if you are interested in discussing some of the topics that you see, of course, you just contact us and we will make some room in the agenda. So they are here until Friday. And so Albert doesn't need much of introduction for many of you, but for the others, he was actually master and PhD student here at IFISC. He obtained the PhD at the end of 2021, and we had the pleasure of supervising him with Gianluca. And the main work was about quantum synchronization, and he started at the end to work on time crystals. And he has spent the last 3 years in Germany, in Tübingen, and collaborating with Federico Carolli and Igor Rezanowski. And now we are actually also together in Quantera project, collaborating in Quantera project. So thank you for coming, visiting us. And,
Thank you. So thanks for the introduction. So it's nice to be here after 3 years, maybe. So I've been working essentially all this time in the University of Tübingen in the group of Igor Rezanowski, and also working in collaboration with Federico. And I will talk about some stuff I've been doing these years that is related to this problem of parameter estimation using the emitted light by collective atomic systems. So in this group, we have been focusing in these collective atomic systems. So this is the outline. I will give a broad introduction on these topics. Then I will present the model we studied in detail, and this is a model that displays a non-equilibrium phase transition. And the phase transition appears in the properties of the emitted light, and I will explain how this happens. And then I will move to the problem we addressed, that is this problem of continuous sensing and parameter estimation. And then I will present the summary and conclusions. So first introduction, I just want to start sketching very broadly our area of study. So we focus on driven dissipative quantum many-body systems. And an example of this kind of systems would be atomic clouds trapped in optical cavities. And in these systems, there are many units. You have dissipation, you have interactions, you have driving. And then in the thermodynamic limit, there emerge some non-equilibrium phases. So you typically can draw a phase diagram varying the parameters of the system, and you will have different phases that can, for instance, break spontaneously some symmetry of the system. And we are focusing on quantum optical systems, and these have the nice property that the non-equilibrium phases in which the system organizes shape the properties of the light these systems emit. And actually, you can place, for instance, if this is a cavity system, which is the kind of system I will focus, you can place, for instance, a photodetector, and you can learn about the phase in which your system organizes by detecting its light. And you can also use this light for applications, for instance, for creating a laser, if you want. And the particular problem I will talk mostly about in this talk is this problem of continuous sensing and parameter estimation. So these driven dissipative systems are open quantum systems. So they emit information into the environment. And as I said, you can monitor this information, for instance, with a photodetector. So the goal of this problem of continuous sensing and parameter estimation is to estimate a parameter or a small perturbation in the system by measuring the emitted light. This is the goal. And the motivation is that if you continuously monitor this information that has been emitted into the environment, you can avoid having to measure directly the system. And you can avoid having to interrupt, for instance, the dynamics of the system. This is one of the motivations. So you have this information that is somehow for free, and you want to use it to learn some property of the system. And some general questions when considering this together with many-body systems is whether there are some phases that are better than others to detect certain kind of perturbations, a very general question is whether quantum correlations in the state of the system can be useful, can enhance your sensitivity, whether a phase transition, so this is usually this is a very sharp change in the state of your system, whether this can be also a resource for sensing. And of course, in talking, you always have to think about which is your actual measurement protocol and whether there exists measurement protocol that is especially good for certain type of phases or perturbations. So these are kind of the general questions of putting together many body quantum systems and this sensing problem. And in particular, we will consider these collective atomic systems. So I will focus strongly on these collective atomic systems. And for this reason, now I want to talk a bit more. I want to introduce more in detail what do I mean by collective atomic systems. And I will present, I will try to explain a bit how they realize these systems in a laboratory. Okay. So this brings me to the topic of atomic clouds trapped in high finesse optical cavities. So essentially, a high finesse optical cavity is a cavity in which the lifetime of the light trapped there is quite long, and this gives the light a lot of chance to, or more chances to interact with the matter that you place inside. And in particular, the matter that you place inside is an atomic cloud, and you essentially trap the atoms inside the cavity using some optical potentials that you can realize, for instance, with laser light. And so this would be an example, well, a cartoon of what do I mean. And then there is this question of why would you put atomic clouds in cavities? So there are a lot of reasons. I give a very concise answer. And essentially, the answer is that the cavity mediates long-range interactions between the atoms. And these long-range interactions are very peculiar in the sense that you can make them not to depend on the distance in between the atoms. So if you think about long-range interactions, you typically think on Coulomb interactions or dipole interactions, and these depend on the distance between the atoms. However, the cavity-mediated interactions do not. They depend only on how the atoms coupled locally to this localized optical mode. And then there is another practical reason, that is that the cavity collects the light that these systems, atomic systems, scatter or emit inside the cavity. So this gives you a means already to study the system through the emitted light from the cavity. And okay, this is a really huge topic. So this is a review. And the consequences of putting atomic clouds inside optical cavities is you can find an immense phenomenology. And it depends a lot on how in which conditions are the atoms. So for instance, if the atoms are in a Bose-Einstein condensate, you can have certain type of phenomenology. If the cavity field is dynamically generated by the scattering of the atoms, or if you drive it directly, is also a very different situation. And in particular, I will focus on a quite simple situation in comparison, which is the one in which at first approximation, you can neglect the motion of the atoms. So essentially the atoms are cool enough and are trapped with an optical lattice tight enough such that at first approximation, you can neglect their motion. And these are sometimes referred as collective dipole systems, and this is what I mean by a collective atomic system. But before moving and further explaining about these kind of systems, just want to give a flavor of what can happen when instead the cavity field is dynamically generated by scattering by the atoms, and the atoms are in a Bose-Einstein condensate. So this is a recent experiment in which they have this situation. So in this experiment, this is the optical cavity. They have a Bose-Einstein condensate, and then they drive the Bose-Einstein condensate perpendicularly. And there is the Bose-Einstein condensate can scatter the light of the perpendicular driving into light inside the cavity. And this leads to an instability that makes the condensate to develop some density pattern. And moreover, what is very interesting of this experiment is that the density pattern is actually varying in time. So you have essentially a way to generate a spatiotemporal dynamics. And as I said, then you can collect the light the system is emitting, and you will see some oscillations that correspond to the frequencies of this spatiotemporal pattern. And also you can study the momentum distribution and you will see it. So, but this is not the kind of system I will study. I just mentioned in order for you to get a flavor of the kind of complexity you can find. What I will consider is these collective dipole systems. And here the relevant degrees of freedom that you have is a selected atomic transition for each of the atoms. So for instance, this typically you reduce the atoms to two-level systems, a ground state and an excited state, and then the cavity light field. And in the ingredients you have still are some form of coherent driving as a laser or an incoherent pumping. You can have interactions, dissipation, and this is enough already to lead to a lot of interesting emerging phenomena. And in particular, in these systems, they have observed synchronization between the atomic dipoles. They have observed collective emission inside the cavity mode, and this leads to what is called a superradiant laser. And they also are able to use this interaction with the cavity to generate quantum states for the atoms, like spin squeezed states. That is an analogous the analogous squeezing, but on the atoms degrees of freedom instead of on the light, or some other quantum correlations. So these kind of systems are driven dissipative quantum optical systems, and the description, they are generally well described by a Markovian master equation. So we don't have closed quantum systems, we have open quantum systems. And in particular, since we are in this quantum optical regime, this Limlat or Markovian master equation usually is a very good description of all these coherent and incoherent processes that are present in the system. And this is, well, it's the quantum analog of a master equation. So this is an equation for the state of your system, a density matrix. And you have the Hamiltonian part, that is the usual Schrödinger equation that describes all the coherent processes. And you have this part here that describes all the incoherent processes. For instance, spontaneous emission would be described by this. And these operators here are usually called jump operators. And for each type of incoherent process you have a label here. So this is the type of equation that describes our system. And now I want to explain a bit better how you describe the atoms in a cavity in this scenario, and how you get these long-range interactions I was talking about, the kind of family of models you can get in these setups. So this would be a cartoon of the atoms trapped using an optical lattice. And as I said, you usually reduce the atoms to just two levels. So each of the atoms is described by a Pauli matrix. And then in this kind of collective systems, it will be important to define these collective operators for the ensemble that are just the sum of all the individual Pauli matrices. And these also you can understand them as collective total angular momentum operators. So the starting Hamiltonian, if you don't have any driving, is just the energy of the transition of the atoms that I can write in terms of the collective ensemble because it's the same for everybody. Then you have the energy of the cavity mode, and then you have the interactions. And the cavity mode is described by a bosonic operator. And then it's important to recall this detuning, which is the energy difference between this transition and the cavity mode, is an important parameter in these systems because it tells you how resonant are in energy the light modes and the atoms. And then the interaction, you can usually reduce it to this photon exchange between cavity and atoms. So we have this sum, and each atom, for instance, this operator means that the atom emits a photon, and the photon is created inside the cavity. And this is the other way around. A photon is destroyed inside the cavity, and the atom is excited from the ground to the excited state. And then, crucially, here we have the interaction strength, and this interaction strength depends on the position of the atoms. And usually in these experiments in which position is at first order not important, what they are able to do is to use an optical trap to position the atoms all in the same, let's say, position of the optical mode. So if you imagine the optical mode in a very simplistic picture, if you imagine it as a standing wave, what they are able to do is to put them all in the antinodes, for instance. And this allows you to make this uniform coupling. And essentially, instead of having to write this in terms of each atom, you can write it in terms of the collective operators. And then, okay, this is the coherent part. And then you have the incoherent processes. And as I said, the incoherent process, you can describe it with these jump operators. And the typical ones that you have is the cavity decay. So the cavity is not perfect. The light cannot stay inside there forever. And this is what this term tells you. So the light goes out with a rate kappa. Then you have a spontaneous emission. If you prepare an atom in the Excited state, it goes spontaneously to another state. And then you have other processes that lead to this dephasing. That is essentially something that destroys coherences. If you prepare the atoms in a superposition state, these kind of processes destroy it. And the reasons behind this kind of term can be very varied. It can be some collisions, some temperatures, some imperfections in the laser. But generically, many things you can model it in this way. So, okay, so this is the starting point. And the point now, there is this mediator. The cavity is like a mediator in between all the atoms. And the point is now how can you engineer long-range interactions between these? So these experiments usually work in what is called the bad cavity limit. So in the bad cavity, what it means is not a bad cavity, but what it means, this limit, is that the decay of photons from the cavity is much faster compared to these other processes. For instance, the interaction in between photons and the light. And this, what makes is, it makes the amplitude of the cavity light mode to be enslaved to the atomic population. So this equality is just for you to understand what does it mean. So essentially, the cavity light amplitude follows adiabatically the dynamics of the atoms. And this means that you can eliminate it from the picture. So if you made this substitution into the previous Hamiltonian and showed, and in the previous master equation, what you get is that the cavity induces coherent interactions and collective emission. So essentially, when you put this inside the previous Hamiltonian, you will get this term here. And this term here is an interaction term between all the atoms. And the interaction strength is given by this sort of resonance that you can turn on and off using the tuning, the energy difference between cavity and atoms. And then there is this other term that is the collective emission. And essentially, this is emission of the atoms inside the cavity. So, or emission, spontaneous emission of the atoms through the cavity. This is more accurate. And this is the rate you obtain. And then, of course, you still have these local processes, but then many of these experiments work in the so-called strong collective coupling, which means that while a single atom is not strongly coupled to the field, once you take into account the whole ensemble is strongly interacting with the field. And in this strong collective coupling, for simplicity as the first approximation, you can also neglect local processes. So the importance of this, you have to take them into account for long times, but there exists a transient dynamics that is well captured by these collective processes. So essentially, we are left with a family of collective models. That is, it contains only the atoms because, as I said, the light follows adiabatically the atom's dynamics. And essentially, we have a collective spontaneous emission. And then we have a Hamiltonian in which we have the interactions that we can turn on and off. And then here I add other typical terms, as this would be a laser driving of the transition with some Rabi frequency, that is the intensity of the drive, and some detuning, some mismatch between the laser frequency and the atoms.
Sorry, Albert, if you don't have the tuning, you don't have this effective cloud, which is physically remaining. So this is the tuning between the active cloud
Yes.
and your development. So they are perfectly tuned. Then you eliminate the.
I don't, yeah. So maybe the intuition is, for instance, if you put a very large detuning, this term goes to zero faster than this term. So this term, some people say is related to virtual excitations of the cavity. So when you are just on resonance, there are no virtual excitations. Everything is inelastic, let's say. I don't know if this gives more intuition. Okay, so now I want to illustrate that actually they are able to realize this kind of, so I will show an experiment in which they study this kind of models. And this, so this group in Chile, in Colorado Boulder, the group of James Thompson, they are, they study many, they have many experiments in which they try to implement different models of this general family I wrote. And they, for instance, work a lot with these strontium atoms, and they are able to create big ensembles of the order of hundreds of thousands. They work with really long-lived, what they call clock transitions. They are able to cool down to this temperature, and with this, just I mean that they are able to meet this condition that position is not bothering at first approximation. They have, well, I have not defined what is the cooperativity, but this means that they have essentially they are able to reach this strong collective public. And in particular, an experiment that I think is very nice is this recent experiment in which they observe a superradiant pulse. So this superradiance is a phenomenon that was predicted I think in the middle of 20th century. And essentially, it means that when you put a lot of atoms together, the way in which they spontaneously emit light is dramatically different than when they are completely uncorrelated. And in particular, when you put a lot of atoms together, there is a burst in the emission of photons. And this is what I explained in more detail here. Essentially, the physics they are able to see in this experiment is the one of just the collective emission term. And the experiment, they essentially take the ensemble of atoms I mentioned, and they prepare them all in the excited state. So since there are no other terms, the stable state is actually everybody in the ground state. So you can represent these states as arrows in the block sphere. So everybody in the excited state is the arrow pointing to the North Pole. And as the atoms decay, you reach the ground state, which is the South Pole. And what they observe is that the way in which the atoms decay, they decay in this superradiant way is completely different as it would if they were independently decaying. And actually, this is what happens is that at the beginning, when the atoms are starting to decay, there is very few photon emission, but the photon emission accelerates a lot, and there is a burst of emission around the middle of the decay, and then it diminishes again. And this is what I'm explaining in words. So these are different moments of time. The different colors are different moments of time of the decay towards the ground state. And essentially, you see that after initial time, there is a very big burst of emission. And actually, if you analyze the maximum number of photons that are emitting, the maximum emitted intensity, and you vary the number of atoms that is involved in this process, you will observe an n squared dependence. So it means that as you increase the atom number, the maximum of emission increases as n squared. And this is a signature of this being a collective effect, because if you had an ensemble of independent atoms, the maximum of intensity could only go linearly with system size. So with this, I just wanted to illustrate that they are able to observe physics related to this collective model up to a certain area at least. So with this, okay, so with this, I want to move to the model I considered, the particular model I considered I will explain the phase transition that it shows, and I will explain the signatures of this phase transition in the emitted light. So the model I consider is actually a paradigmatic collective model, and in which you have only two ingredients. You have a resonant laser driving, which is this with Rabi frequency omega, and you have this collective emission. And recall that we are dealing with this collective ensemble. So this model has a long history, and in particular, there is this old paper in which it was studied in detail. And actually, the dynamics for large system sizes, you can understand them essentially with a mean field approximation. So in the thermodynamic limit, what you would do is, well, you derive the equations of motion for the magnetization, and you do the infinite approximation of breaking when you have two operators, you break them in expected values of one operator. And for convenience, I also define this normalized magnetization that goes in between -1 and 1. So essentially, for large system sizes, the dynamics can be understood with these three equations. And these three equations live on the Bloch sphere in the sense that total angular momentum is preserved. And a very easy way to understand the dynamics is to recall that this system has a symmetry. So you start with an initial condition with zero magnetization, it remains there. And then by using spherical coordinates, you can reduce this system of equations to this equation for a phase. And this is essentially this equation for a phase where it has this term and this sine term, and it's essentially this equation has an infinite period bifurcation. This means that if the Rayleigh frequency is smaller than the critical one, this equation has fixed point solutions, while if it's larger than the critical one, this equation has only oscillatory solutions. And indeed, well, this is what you observe. For Rayleigh frequency smaller than the critical one, the system goes to a stable fixed point with negative magnetization, so always living in the south hemisphere of the Bloch sphere. And as you increase the Rayleigh frequency, you reach the equator, and then the system, there is a phase transition in which the system displays these oscillations. So this is a model that was studied a long time ago, but is perhaps the simplest model in which, one of the simplest models in which you have a spontaneous time translation symmetry breaking. So with this, I mean, you have a master equation that is independent of time. And as you go to the thermodynamic limit, you have the emergence of a limit cycle or of non-decaying oscillation. And there was a lot of interest for, or there is a lot of interest for systems breaking this symmetry. And these are sometimes known as time crystals. So time crystals would be a quantum system, a quantum many-way system that breaks this time translation symmetry. So in the talk, I will use oscillatory phase or time crystal phase to refer to the phase displaying oscillations. And here I want to comment because I explained the dynamics in this limit, but actually I will focus all the time on the finite size, on systems of finite size. So I want to explain briefly the signatures of each regime for finite sizes. So for finite sizes, the oscillations decay. So there are fluctuations, in particular there is phase diffusion, and the fluctuations have a finite lifetime. So what you find is, this is the typical dynamics in the oscillatory phase. This is the Z magnetization or the Y, you can see. But the point, the signature of this eventual time translation symmetry breaking is that the lifetime increases with system size. Yeah.
The decays, because it's something that is not in your equation that you showed before.
Yeah.
So the thing that not decay.
Is in the master equation. So
It's not.
So it's here.
So this equation that applies to the hemodynamic limit, comes in the master equation has no dissipation, or why did it not decay with the hemodynamic limit?
So in the thermodynamic limit, essentially, the equation, the emergent attractor is a limit cycle.
Yeah, but the decay that you observe in the master equation with finite sizes is because there is some dissipation of energy.
Yes.
And if you have no decay in the thermodynamic limit, but there is no dissipation.
There is.
So
you increase the energy in here.
yeah, I mean, so the thermodynamic.
Well, the mechanism one, because I'm making the number of particles, I don't see why there is no dissipation. I mean, why the dissipation disappears when there is compensated.
So let's say the way I see this is you would have a nonlinear equation that has limit cycle, and there is a noise term. And yes.
The energy and when you observe is not symmetric, that decays to
Yes.
Now you increase the number of atoms, and they understand in the limit in which you have many, the symmetry will not be.
Yeah.
So what compensates to decay, what complex is the energy that is lost?
So there is, I mean, you are putting, there is energy entering through the laser driving.
And this amount of energy that we inject is proportional to the number of atoms.
Yeah. If, yeah, yeah. So if you want to be rigorous on the definition of the thermodynamic limit, then you need to put a 1 over n somewhere, because otherwise the energy is infinite. But
and the object would be different, and then the thermodynamic.
No.
Change the 1 over n.
I would say no.
This is, you have to do the energy, but you have to rescale the environment. Control the environment.
So that, but then it's there should be some mechanism, okay, in which you keep adding more and more energy. That is what prevents that the dissipation takes on. Not that I understand.
I don't know how to answer this question.
Okay, please continue.
Yeah, okay. No, maybe later I have a better answer for this. Okay. So for final sizes, the oscillation of decay. And well, for final sizes, you also have a crossover rather than a phase transition. So the master equation has a for final sizes, the master equation has a stationary state. And you, for instance, here I compare the magnetization computed in the stationary state in the red line, and in the dashed line, I compute the prediction for the mean field. And this is just to say that at the mean field level, you will have a true non-analyticity at the critical point, but for the master equation, you will observe a crossover. Yes. So dissipation is a spontaneous emission to the environment.
This is something about fluctuation.
Yes. So yeah. So how I understand it is that for the limit cycle, let's say, I imagine the following situation: you have a nonlinear equation that has a limit cycle there, and you have a fluctuation term, a noise term, and this noise term induce phase diffusion. So if you take the average over trajectories, you will see decaying oscillations. And the point is that what I imagine is that the amplitude of this noise term goes as 1 over the system size.
That's why I keep doing okay, so
yes.
That's an average that it gave.
Yeah, exactly. So sorry if I didn't explain that. So the dominant fluctuation process is phase diffusion. And this, let's say, dies out if you are able to put infinite particles. This is the thing. Okay. So I will focus on the final size behavior. And as I said, the phases imprint. So this dissipation term is a spontaneous emission into the environment. And therefore, what we can expect is that the different phases imprint different properties in the emitted light of the system. And we can study the emitted light at different levels. We can study it at the average levels with the properties we get from the master equation. And this gives us access typically to the average emitted intensity or the first and second order coherence functions. But we can also imagine that we can do this thing called continuous monitoring, in which you put a photo detector that has it needs to have a high efficiency, and then you can monitor in real time the amount of photons you are getting from the system. And if this allows you to model, let's say, single experimental realizations, and instead of studying the master equation, you study some stochastic process induced by your detection scheme. At the average level, this description recovers this one, but modeling also this stochastic trajectory gives you access to the stochastic process that, for instance, photo detection is induced. So I will show signatures of the different phases in the emitted light at these two levels. So the first one is at the average level. So this could be recovered, for instance, again, with a photo detector and taking a very long average of the number of detections. And what you can show is that if you take a very long average of the number of detections, you essentially recover the emitted intensity of the system. And this already contains signatures of the phase transition. And this is what I show here. So here I show many things, but first let's focus on the green dashed line. So this is this emitted intensity by the system in the stationary state. And I show it for a system of 100 atoms. And this is the phase diagram. So I have the stationary phase in the stationary regime for this below 1, and the oscillatory regime for this radio frequency above the critical 1. And what you observe in the line is that it displays a crossover between these regimes. So it displays a different behavior in both regimes. And actually, the black lines are an analytical expressions in the thermodynamic unit obtained by Carmichael. And there what you see is that there is actually a non-analytical change in the emission intensity. So this is, you can take it if you want as an order parameter or an indicator of the phase transition. And what is really interesting, what reveals a lot about the two possible phases, is to decompose the emitted intensity into a coherent part and an incoherent part. And the coherent part comes from a scattering of the input laser, and is essentially defined as the squared amplitude of this monetization operator, while the incoherent part is given by these variance. So this is what I show. I show the coherent part in blue and the incoherent part in orange. And essentially you see that the incoherent light is 0 in the stationary phase. And essentially all the intensity is given by the coherent part. So essentially in this phase, what's happening is that the atoms are essentially scattering all the light you are sending to them with a laser. Instead, after the transition point, the atoms are not able to scatter all the light and they start absorbing and re-emitting. And this is why after the transition point, essentially it's a sort of many body saturation point in which the coherent component diminishes. And now we see this kind of second order phase transition profile, this kind of profile on the incoherent light. And I don't write it here, but the interesting thing is if you see I rescaled all the quantities by n squared. So essentially in this regime, the incoherent light is proportional to n squared. And if you write down these operators in terms of each atom operator, you find that the only way to have this incoherent intensity proportional to n squared is that there are atom-atom correlations. So in this phase, essentially, you have significant atom-atom correlations. And this, if I later, when I explain some results from parameter estimation, it's important because this is actually a resource for you being sensitive to external perturbation, as I will show. So then, well, maybe I speed up a bit. So then I show some results of, so this was properties at the average level of the emitted light. And then I will just show what will happen if you have, so now you have this photon counter outside and you observe a single realization of the photon counting process. And I assume that I have unit efficiency. So this is ideal. I have a perfect photodetector and I just detect the emitted light. And I will just show an example. So these are so-called quantum trajectories. This is the magnetization. They follow a stochastic process induced by the photodetection. And the actual experimental observable is the photon count. This is the number of photons you detect in per unit of time. And here I show 2 points. I show 1 point in the stationary phase and 1 point in the oscillatory phase. So in the stationary phase, essentially the system reaches a fixed point. And it is interesting to notice that this actually is in a stochastic trajectory. So this fixed point this stochastic trajectory for the magnetization reaches some sort of absorbing state. And at the magnetization level, it doesn't display fluctuations. However, if you look at the photon count, you see fluctuations around an average value. And then it is interesting that for the oscillatory phase, for the time crystal phase, even for finite sizes, when you study the photon count, the photon counting process, you don't see decaying oscillations. What you see is oscillations that are essentially phase diffusing. So essentially what this reverse gives you very clearly is that actually the decay is induced by this phase diffusion process, in which the phase diffusion is induced by the fluctuations. And okay, you see these oscillations in the magnetizations and also in the number of counts. And actually here is not very clear, but if you make a Fourier transform, you will see that there are peaks of this photocounting signal at the frequency of the limit cycle. And actually, as what I was saying before, is that as you increase the system size, the quality factor of these peaks increases. So the frequency over the decay rate increases linearly with system size. So then there are other signatures, but I will skip it because otherwise I cannot talk about this. So now I explained you that this system has this non-equilibrium phase transition, and I showed you some of the main signatures of these signatures of the stationary regime and the oscillatory one in the emitted light of the system. And now I want to address this problem of continuous sensing and parameter estimation. So let me start making how you usually the general statement of the problem. So the general statement of the problem is that you have an open quantum system that you have is a well-controlled open quantum system in the sense that you have knowledge, a good knowledge of the main coherent and incoherent processes that occur in the system. You know how the system behaves. And then there is a perturbation, and this can appear as a small extra Hamiltonian term. And then the goal is to try to estimate the size of this perturbation. And so these are some common examples. Common examples could be try to estimate a small frequency difference with a reference oscillator, try to estimate a weak electromagnetic field. So in this case, this perturbation would be proportional to one of the magnetization and with a small amplitude, try to estimate a small phase. These are common examples. And as I said, I'm focusing on not measuring directly the system, but measuring the light the system is emitting. So I want to study how sensitive I am to a specific type of perturbations by studying the emitted light. This is what I want to do. And then in quantum systems, there is a fundamental bound on sensitivity. So the precision by which you can estimate the perturbation is not infinite. It's actually finite and is related to the state of the system you are trying to probe and the dynamics that is generating the perturbation. And there is a very general quantity called the quantum fission information that allows you to quantify the sensitivity. So essentially here I've written a way to compute this fission information because I think it's very illustrative. So essentially the fission information, the sensitivity of your state to a parameter change in the parameter G, so a small parameter change delta G, is given by 1 minus the fidelity in between your state evolved with the parameter G and your state evolved with the parameter G plus the perturbation. So this fidelity takes the value 1 when the states are the same. And it's a quantity between 0 and 1. And the more different than the states, the smaller is the fidelity. So essentially, you can see that the biggest is the change in the state for a small change in the parameter. The smaller is this fidelity, and the bigger is this fission information. So this fission information is quantifies the sensitivity you have on perturbations of a specific kind. And then there is this thing called quantum Kramer-Rao bound that links this fission information to your parameter estimation problem. So when you measure a quantum system or when you measure the light emitted by a quantum system, this is the outcome of the measurement is stochastic also. So when you characterize it, you have to characterize it statistically. So when you estimate the value of a parameter, your precision is given by the variance of, so I got 2.0 with the variance 0.01. And what it tells you this quantum Kramer-Rao bound is that the variance of any protocol, measurement protocol that you can imagine, that is a valid measurement protocol, is lower bounded by the inverse of the fission information. So by computing this quantity, you can obtain a very general statement of which is the maximum precision you can get into into estimating the parameter. Then, of course, the different question is to find the actual protocols that can become close to the bound or not. But analyzing the bound gives you some important general answers. So a bit the toy problem we set is, okay, we have two parameters in our model. So we will set the goal to estimate the radio frequency. It's a protocol based on emitted light. So in principle, the idea is we know we have a prior knowledge of which is the value of the radio frequency, and we want to know which is our sensitivity to determine small variations around the previously known value. And the general question that we did this because our interest was in seeing how this sensitivity could change along the phase diagram, and in trying to understand how the different collective effects or the different effects present, dynamical effects present in the system could play a role in this sensitivity. So there are two approaches. The first one is related to this quantum feature information. So in the first one, you try to answer the question in a very general way. You compute this very general quantity and you obtain a bound. And the bigger is this quantum feature information, in principle, the more sensitive is your system. But this tells you nothing about how could you exploit this sensitivity. So there is the second approach that is choosing a specific measurement protocols and seeing whether they are able to get close to the bound or whether they are able to exploit some characteristic of the bound. And so I explained the results for the first approach, computing the feature information. And as I said, the feature information depends on the state of the system, on the state you put there. And as we are interested in protocols that use information contained in the emitted light, well, we have to compute the feature information of this joint state of the system and the information it has emitted to the environment. So this is a very complex object. Usually you cannot compute it, but in these papers, they found a way to compute the quantum feature information of this object using only a sort of master equation. So they provided a feasible way to compute this. And then essentially any protocol you can imagine that measures in whatever way the light that has been emitted is fundamentally bounded by this object. No, it does not apply. So this only applies to systems that can be described by a marker. No. Yes. Systems described by this master equation. In this scenario, if you measure the light in this scenario, this bound applies. But yeah, it's only in this scenario. So in the long measurement time limit, I write here the square root because sometimes I compute standard deviations. In the long measurement time limit, essentially this quantity is dominated by the information emitted in the environment, and it displays this scaling in time. That is it's called the standard quantum limit scaling, and it has some prefactors. So this is essentially in this kind of measurement scenarios I'm imagining. Essentially, the measurement, the observation time plays the role of sample size. So the larger is your measurement time, the more sample you have. This is why you find this kind of scaling with time. So essentially, what can vary along our phase diagram is this quantity here. And this quantity is the one I characterize in the next slide. So this is what I characterize here. So I plot this prefactor along the phase diagram. And I observe two very distinct behaviors. I also change the system size. And what I observe is that in the stationary phase, there is a region, a big region that approaches this critical point in which this is constant. This is independent of the Rabi frequency. And it's also independent of the system size. And instead, in the oscillatory phase, in the time crystal phase, you observe this kind of profile that is similar to the one of the incoherent light that I showed before. And as you increase system size, your feature information increases. And this is what we try to determine here. So we could compute this quantity more or less up to size 100, and we try to get the scaling of this with system size. And what we observe is that if you take a point in the stationary phase, it's constant. At criticality, this prefactor goes more or less as square root of n. And in the oscillatory phase, which we choose this point, but you can choose other points, the prefactor goes linearly with system size. And this means that the Fisher information in this phase behaves, the scaling of this Fisher information behaves as n squared times t. And this n squared has a name, is called Heisenberg limit in particle number, because typically you can only achieve this kind of scaling with your particle number when either you have states with some specific type of quantum correlations, or when you are dominated by some useful collective effect, which is the case. So actually, the message here is that near the critical point and in the oscillatory phase, particle number is a resource, in the sense that as you increase it, you make your system better for sensing perturbations of the value omega. Instead, in the stationary phase, for the properties of the emitted light, it has no effect. Essentially, you don't improve by increasing the system size. So now, I just explained two protocols we tried to see if they could display a similar sensitivity as the one of the Fisher information. So now I go to the second approach. So a very simple protocol could be based simply on taking the average intensity, which is related to what I said previously. So this system emits photons. I take a long average, and then I try from the value I get from the value I get from intensity, I try to estimate the value of the Rabi frequency. And then the error I will commit, the standard deviation, will be, for a single long run, will be related to the variance, the square root of the variance of this quantity, and the susceptibility of this quantity on changes on the parameter of interest. And this protocol is lower bounded by the Fisher information that we just started. So I show the results of this protocol for, this is a system of size 30 atoms. So I plot, essentially I plot the results corresponding to the precision of this protocol in a red line, and the precision given by the bound, so the fundamental precision that we could achieve, in a dashed black line. And let's say the smaller, the less error I have. And essentially what I see is that in the stationary phase, this simple protocol of taking a very big average works. So it saturates the bound, while at the critical region and in the oscillatory regime, it behaves in the opposite way. So in this regime, in principle, you have more sensitivity, but if you just take the average photon number that you detect, you just don't get it. And you just get the opposite behavior. And this is probably related to the fact that the collective effect that you have in this regime are the oscillations. So you need to make something that resolves these oscillations. This is the explanation I got. And okay, in our work, we found a good protocol that actually could resolve almost saturate the optimal bound, and it's very complicated. It requires using other systems to probe this one. So here I just want to report on another protocol that is very intuitive in the sense of telling you which is the resource that you are making use of for sensing, which is actually these collective oscillations. So essentially this other protocol is based on putting the output light emitted by your system through an interferometer, in which it picks there is a path difference. And essentially when you detect photons at the output of the interferometer, you will see an interference pattern. And this interference pattern is related to the oscillatory dynamics of the system. So the oscillation in the interference pattern in the intensity is related to the oscillations we saw before. And the observables you have access to, putting photon counters here, are, for instance, the number of photons you detect in the number 4, in the N4, the number of photons that you detect in the number 5, or the difference in the number of photons you detect in both photodetectors. All of them give more or less the same result. For this, when you can write some analytical approximate expressions. This is the one giving more intuition. So essentially, the intensity, the number of photons you detect, the photon difference that you detect is essentially proportional to these two time correlations. And this resolves the collective dynamics. And tau here is fixed by the path difference. So you fix the path difference in the interferometer in order to match a point in the oscillation. And this is what I wanted to illustrate in this picture. Let's see if I manage. So this shows, this is the expectation value that you would obtain in red with the photon difference, in green with the photon at number 4, and in yellow with the photon at number 5. So imagine you have tuned your system to sense perturbations around the value right frequency over critical one equals to 2. So essentially what you are doing, you have an interference pattern, and you have essentially tuned the path difference to be in the maximum gradient of the oscillation. So then a difference in the frequency of oscillation, so the frequency of oscillation depends on the right frequency, a difference in that frequency of oscillation translates into a big difference in the intensity, the detected intensity. And actually, if you make the statistics of the measurement and you see the error, the estimation error, what you will see is that it's not optimal. So this does not saturate the bound. However, it displays the same as scaling. And actually, you can do some approximate expressions. And this is the variance of your estimation for the value of the right frequency. And essentially, there is a noise term. So there is this term comes from the let's say the variance on the top of the quantity you are measuring. And this comes from the susceptibility of the quantity you are measuring to changes in omega. And this is independent of the path difference, but this you can tune it to this maximum gradient point. And actually, you can obtain an approximate expression for this difference, and it's this one. It's essentially the incoherent intensity multiplied by this factor. So this factor is an interference term, but if you compute the size of this factor, if you take this derivative and you put all the numbers, this is independent of system size. So this is just a number. Instead, this incoherent intensity is what gives you this n squared in the susceptibility. And if you remember, this comes from this oscillatory phase having all these atom-atom correlations. So yeah, with this, so I hope I transmitted you how you can engineer these collective atomic systems using optical cavities, that the emitted light of these systems contains signatures of the different phases in which they organize. I explain you which is this problem of parameter estimation, and I show you how collective effects as these oscillations can lead to enhanced sensitivity to detect a specific kind of perturbation. So thank you for your attention.
Thank you for that.
Yeah, thanks.
Any questions? There are more? Richard? Luisa?
I just want to try this phase transition between the stationary and the oscillatory regime. Is there any difference of that and the threshold of a laser, or is it
Is there any? Sorry?
with
the threshold of a laser?
Yeah, or is it a different name but the same phenomena?
I don't know, because in the transition to lasing, let's say, because here you have a coherent driving, you have already a laser there, and it's already, and you increase the power, and let's say the system at some moment can no longer, so the system tries to scatter the light from the laser, and there is a moment in which the atoms saturate, are not able to scatter anymore because the light is too intense, and it starts oscillating. I think instead on a lasing, it's like you have some population inversion, and at some moment is enough. There is something that becomes in. I don't.
But you also have like a kind of a creation of a limit cycle.
Yeah, no. It's a creation of a limit cycle. Yeah. In this sense, it's the. Yeah.
Hey, thanks for your nice talk. This question is, I think, is a bit technical, but how do you compute this quantum feature of the state of the emission plus
Yeah.
the atoms?
So I don't know
If you can say, I don't know, maybe it's too difficult.
Yeah,
but-
no. Actually, let's say. Actually, it's kind of, you don't need, the trick is that you don't need to explicitly model the environment. This is the trick.
Mhm.
So the trick is also related to the previous question. This only works in a situation in which you have these Born Markov approximations.
Yes.
And in these situations, you can, so this would be in this approximation, in this Born Markov approximation, this would be an expression for this system environment state. So you can write it in this approximation
Mhm.
as the state of the system. You can discretize the emission field. So not the environment. You discretize, it's like the input output format. You discretize the emission field.
Mhm.
And as time passes, you discretize time. And as time passes, you make this sort of collision model process. And this is a pure state. And from this, you can compute the Fisher information. You don't need to compute explicitly this state. You plug in this formula that is generically valid in the Born Markov regime. And when you compute the Fisher information for this general state, you end up finding that the explicit calculation only needs of a sort of master equation. So you can also in the calculation of this Fisher information, you don't need to account explicitly, you don't need to compute this explicitly. You end up with a sort of master equation.
So this is not related to a specific dissipation.
It's not
It is not related to the microscopic origin of the dissipation.
No.
It's just putting a collisional model that would give the same effect
yes.
of the dissipation.
So you need for this reason is really this input output formalism. So you really need to be able to describe your system with a master equation. Otherwise, it does not work.
Okay.
Yeah.
Okay, because here, as you are accounting for the atoms in the cavity, okay, maybe for me it's kind of weird because I think what we would like is just to measure the environment, let's say,
Yes.
somehow, and leave the atoms alone.
Yes.
But as far as I understand from what you say, this is the whole system.
Yes.
Also with the atoms.
So you can also refine this information
Okay.
and compute it just for the environment.
Yes.
But also importantly, if you compute the one from the system and environment, the important thing is that for long times, you can show that this is dominated by the contribution in the emission.
Okay.
Because let's say the part of the emission becomes extensive with time.
Okay.
So you could refine the measurement and compute it also, and this is done in some papers, a comparison.
Yes.
And you find that there is just a small constant for long times because it's dominated by the field.
Okay, thanks.
More comments or questions? Maybe just a last comment about this detection scheme. So you were telling if you just do photo detection, you are very far from the bound. If you do this 2-time photo detection, then you can go down.
Yeah.
If you do homonine detection,
So I guess, the problem was not to do photo detection, was to take these averages, long time average. So homoline detection, I also tried in the beginning in the sense I tried to make a long time average and it didn't work either because I was averaging out the
or the
oscillation.
oscillation.
So
Okay.
the point of this scheme is you have to find a way to measure something related to the oscillations. Then it will probably work.
The Fourier transform of the average.
The Fourier transform I tried, but
Okay.
it was complicated. So
Okay.
it was not working.
Okay. More comments or questions? If not, let's thank Albert again. Now, for people interested, there is another talk of Robert. It is first PhD students in the Tübingen group. So we will continue this. And we will stop, unless there are questions from the participants online. I didn't ask, sorry. Shout if you have questions. And if not, let's conclude with the recording. Yes, we are not having the Zoom for this. Maybe we can have just 1 minute of pause from the group. It can remain open, yes. So we will wait just 1 minute if you just need to go to the toilet to be ready. It's time.